Good afternoon, everyone. In this project, I develop a machine learning model to predict loan default risk using the home credit dataset. The goal of the model is to determine whether a loan applicant will repay a loan successfully or default. Credit risk prediction is very important application for machine learning because lending decisions affect real people's access to financial services. Because of this, the focus of the project is not only predictive performance, but also responsible AI principles such as fairness, transparency, and interpretability. In addition to building a classification mode, I also analyze how the model makes decisions and whether the prediction could introduce biases across different groups of applicants. The data set used in this project is derived from home credit default risk dataset. Each row represents a loan application and include demographic, finance, and behavioral information about the applicants. The target variable is called target, which with the capital letter, and where zero means the applicant successfully repaid the loan and one means the applicant defaulted. The training data used in this project contain about 5,800 observations and more than 100 defaults. One important characteristics of the dataset is that the highly imbalanced. Most applicants repay their loans successfully, while only small portion of actually defaults. Because of this imbalance, metric like accuracy alone are not sufficient of evaluating model performance. Instead, metrics such as ROCAUC and average precision provide more meaningful view of how well the model distinguish between high risk and low risk applicants. Before training models, several processing steps were applied. First, the ID column and target variable were separated from the feature set. Then the data was split into training and validation set using 8-20 split while preserving the class distribution. After splitting the data, missing value were handled using different strategies depending on variable type. Numerical features were inputted using the median value, while categorical features were filled in using the most frequent category. Since machine learning model cannot directly process categorical variables, categorical columns were converted using one-hot encoding. Finally, the training, validation, and test feature set were allogened so that they all contain the same column and feature structure. For the model itself, I choose random forest classifier. Random forest is a strong baseline model because it can capture nonlinear relationship between variables and generally robust, no noise in data. Another advantage is that tree-based model were well with explainability tools such as SHAP. The random forest model in this project uses 300 trees with limited maximum depth to control overfitting. Because the dataset is imbalanced, class weight were also applied so that the model pays more attention to minority default class. To evaluate the model robustness, I also performed fivefold cross-validation on the trained data. The average ROCAUC from cross validation is around 0.7, which indicates that the model is relatively stable ranking performance across different training splits. After training the model, I evaluate the performance of validation dataset using several metrics. The accuracy of the model is around 0.89. However, because of the dataset is balanced, accuracy alone does not tell the full story. More informative metrics include precision, recall, and ROCAUC. The model achieved ROCAUC about 0.74, which suggests that it has reasonably ability to distinguish between risky and safety borrowers. Precision and recall for the default class are lower, which means the model still missing some true default cases. This is common in imbalanced classification models. To better understand the model's performance, I examined the ROC curve of the precision recall curve. These visualizations show how the model balance false positive and false negative were when predicting default risks. In addition to evaluating the performance, a major focus of this project model interpretability. First, I examined the feature importance score from random forest model. The most influential feature including external credit score availability, such as EXD score 1, EXD score 2, and EXD score 3, as well as employment history and age-related variables like days employed and days birth. These results are intuitive because external credit scores and employment stability are strong indicators of financial reliability. To gain deeper insight into how the models make prediction, I also applied SHAP values, which provide both global and local explanation of model behavior. The global SHAP summary plot show how which variable contributes most strongly to predictions, and whether higher or lower feature value increase or decrease predicted risk. The visualization helps explain why the model identifies certain applicants as higher risk. In addition, partial dependence plot were used to show how predicted default probability change as specific feature vary. Together, this explainability technique improve transparency and make the model decision easier to understand. Another important component of the project is fairness analysis, because the credit scoring model can affect access to financial opportunities. It is important to evaluate whether prediction differ across demographic or social and economic groups. In this analysis, I explain predicted default rate and errors rate across several grouping variables, including gender, family status, income type, and ownership of assets such as cars or properties. For example, the model predicts slightly higher default rate for male applicants compared to the female applicants. However, when comparing these prediction to actual default rate in validation data, the observed default rate is also higher for male applicants. This suggests that the model may be reflecting patterns present in the data rather than introducing clear discrimination behavior. So even so, the analysis highlights the difference across group to exist, which means fairness monitoring should be an ongoing part of the model government. For the ethical perspective, automate credit decision systems must be used carefully. A false positive prediction could incorrectly classify the reliable borrowers as higher risk and then deny them access to credit. On the other hand, a false negative prediction could approve a loan for someone who's likely to default, creating finance risk to lender. Because of these consequences, machine learning models should not be treated as fully autonomous decision maker. Instead, they should support human decisions making and operate with clear policy guidelines. Responsible AI practice, such as transparency, fairness analysis, and performance validation, helps ensure that models are used responsibly. Finally, before employing the model, I like to this real finance system. Several consideration are necessary. This include monitoring data drift over time, periodically retraining the model as new data become available. Performance fairness audits to detect emerging biases, such as maintaining documentation for regulatory or governance purpose. Human oversight should also remain part of decision process, especially for high impact financial decisions. In conclusion, the project demonstrates how machine learning model can be developed for credit risk prediction while incorporating responsible AI principle. The random forest model achieve reasonable predictive performance and provide interpretable insight to feature importance. SHAP explains explanations and partial dependence analysis, fairness analysis also helps identify potential disparities across application groups. Overall, this workflow highlight the importance of balancing predictive performance with transparency, interpretability, and ethical considerations when applying machine learning to real-world finance problems. Thank you.